Hello everyone, I hope you're doing well and welcome back to my channel. In this video I want to prove a theorem about the relation between closedness and compactness. But before watching this video, make sure to like, comment and subscribe to my channel so you can see more content from me in the future. Okay, now let's get to this theorem. This theorem basically states that closed subsets of compact sets are compact. Okay, to prove this theorem, let's suppose F to be a closed F to be a closed subset of compact set K, and let's prove F is compact. Okay? To prove F is compact, what I have to do is that I have to prove that every open cover of F has a finite subcover. Okay, now let's suppose V sub alpha, the collection of V sub alphas, is open cover for F. Okay, so the collection of V sub alpha is an open cover for F. From the hypothesis, I know F is closed, so F complement is going to be open. So F complement is going to be open. But I can conclude from these two statements, I can tell because the collection of V sub alpha is open cover for F, and F complement is an open, then I can tell the collection of V sub alpha, the collection of V sub alphas union F complement is open cover for K. Open cover for K. But the question is, why is it open cover for K? As you know, because F complement is open and the collection of V sub alphas is open cover for F, then the collection of V sub alphas are going to be open sets. And I know the union, infinite union of open sets at the end going to be an open set. So this set that I'm going to underline it is an open set that can cover K. And because K is compact, then every open cover is going to have a finite subcover. Okay? So I can tell this open cover has a finite subcover. For example, V sub alpha sub 1, V sub alpha sub 2, and blah blah blah, V sub alpha sub n with F complement is a finite subcover for K. Okay? But from the hypothesis, I know F is also subset of K. Then this finite subcover is going to be also a subcover for F. Okay? So because F is subset of K, then I can tell this finite subcover is going to be a subcover for F2. V sub alpha 2, blah blah blah, V sub alpha sub n. F complement is a finite subcover for F. Subcover for F. For F. But if you be careful, you're gonna see because the intersection of F with F complement is an empty set, because the intersection of F with F complement is an open set, then I can eliminate F complement from this subcover. Okay? So I'm gonna write it because the intersection of F with F complement is an open set, is an empty set, then I can eliminate this F complement from the subcover. You know, just to prove it geometrically, let's look at this Venn diagram. And if you see, for example, if this is A and this is B, as if this set is C, as you can see, A and B are open cover for C, and because the intersection of C with B is an empty set, then I can tell A itself is an open cover for C. Okay? So I can eliminate F complement from this subcover. And I can tell V sub alpha sub 1, V sub alpha sub 2, and blah blah blah, V sub alpha sub n is also a subcover for F. Is also a subcover for F. Okay? Subcover for F. What I basically did, I supposed V sub alpha to be an open cover for F, and I could prove that this open cover has a finite subcover. So right now I can tell that because every open cover of F has a finite subcover, then F is compact. F is compact. Okay. Now I prove this theorem.